Hello, my name is André Pacak, and today I'm going to talk about our paper, A Systematic Approach to Deriving Incremental Type Checkers. And this is joint work with Sebastian Erdweg and Tamás Szabó, and we are all from the Johannes Gutenberg University Mainz in Germany. When we as developers program, we are guided by the feedback the IDE gives us. And this feedback includes typing errors or code completions, for example. And it's crucial that we receive this feedback fast, because otherwise it either becomes obsolete or it slows the development process down. And an IDE derives this feedback based on the type checker implementation of a programming language. Take the programming languages Java and C# as an example. They are very similar in the typing features they support. Java has three major IDE implementations: IntelliJ, Eclipse, and NetBeans, where C# has two, Rider and Visual Studio. All of these 5 IDEs implement fast type checkers for similar typing features, and this is a lot of implementation effort. The ideal solution would be to take the language specification of a programming language and systematically derive a fast type checker based on it. In this paper, we explore one possible solution. And our goal is to translate the language specifications, and in particular, the typing rules, and translate them to Datalog. And we chose Datalog as a target because we can piggyback on Datalog's efficient incremental execution model. This means Datalog only has to process the changes of the input to update the output. And if it's possible to describe a type checker as a Datalog program, we get an incremental type checker that only has to process the change in the AST to update the typing information, instead of retyping the whole AST all over again. So Datalog is a logic programming language, but it is limited. It's limited because it can only derive finite relations. And the reason behind this limitation is that Datalog tries to exhaustively enumerate all derivable tuples. And if there's an infinite number of derivable tuples, then the Datalog program will not terminate. So the question is, what are the threats to finitely encoding the typing relation? The first question we have to answer is, if expressions are a threat to finitely encode the typing relation. So here we have the typing relation as a table, and we can arbitrarily nest lambda abstractions. Therefore, there's an infinite number of well-typed expressions, so the complete typing relation is infinite. And Datalog will try to exhaustively enumerate all these infinite tuples, but this will never succeed. But there is an existing solution that is used when doing static analysis in Datalog. We only consider the expressions that are actually part of the user program and not all possible expressions. Take this nested lambda expression as an example. We only consider the expressions that are needed to describe the whole expression. So the number of expressions that Datalog has to consider is finite. Now let's check if types are a threat to finitely encoding the typing relation. Take the identity function as an example. It can have an infinite number of types associated to it, as long as the type maps to itself. So hence, Datalog cannot exhaustively enumerate all tuples of the typing relation. In our work, we assume an algorithmic type system, which means that the expression uniquely determines its type. And in Datalog, this is called a functional dependency, where Datalog now only has to consider one type for a given expression. Therefore, types are not a threat to finitely encoding the typing relation. Now let's see if contexts are a threat to finitely encoding the typing relation. As an example, we check what the typing of variable x is. So x has different types associated based on the context it is considered in. And in an algorithmic type system, there is a functional dependency where the expression and the context determine the type. But there is an infinite number of contexts to consider. So the functional dependency is not sufficient enough to restrict the typing relation to a finite number of tuples. So the context is a threat to finitely encoding the typing relation. So the question is, how can we actually encode it then? How can we use Datalog? And in our paper, we found a way of finitely encoding the typing relation. And it's based on two observations of algorithmic type systems. First, each meta variable in the typing rule is uniquely determined. And second, each node in the AST is visited at most once. So therefore, the context under which an expression is typed is uniquely determined. And we utilize these observations to decompose the typing relation into two separate relations. One for passing the context to the expression, where the expression uniquely determines the context, so this relation is finite. And another relation for typing the expression, where the expression uniquely determines its type, and therefore this relation is also finite. So both relations are finite, and Datalog can be used to derive these relations. And so it will terminate. And based on this decomposition, we can systematically rewrite the typing rules such that it describes these two relations. Take the variable reference rule as an example. We rewrite it in such a way that it uses the context relation to get the context under which the variable is typed, instead of getting this explicitly passed context as it was before. At this point, we systematically derived an incremental type checker by translating to Datalog. And based on this type checker, we performed micro benchmarks on different programs. And we measured the initial and incremental update times for different changes. And we categorized these changes into low and high impact changes. High impact changes affect a lot of tuples in the typing relation when doing a small change, where low impact changes only affect a small number of tuples when doing a simple change. For low impact changes, we had a speedup of roughly 13,000x. But for high impact changes, we only had a speedup of 1.4x to 7x. So the type checker in Datalog is indeed incremental, but it is not as fast as it could be. So naturally, the question arises, how can we improve the performance of these type checkers in Datalog? And we have identified two scenarios where our derived Datalog type checkers behave suboptimally. And to illustrate the first scenario, let's have a look at the let expression, which binds the identity function for unit types to ID. And during typing, we propagate the extended context to all the sub-expressions of the body of the let expression. But when we change the expression bound to ID to the identity function for not types, for example, we need to redo the typing derivation for the body of the let expression. And we do it with the new context. And this leads to unnecessary retyping, especially if ID is never referenced in the body of the let expression. To optimize the first suboptimal scenario, we found a new encoding of type systems in Datalog. Let's have a look at the rewritten variable reference typing rule we have already seen earlier. It builds up the context and then searches within that context when a variable is referenced. And the idea of our encoding is to eliminate the context entirely, and instead we fuse context buildup and context lookup into one find relation. And this relation searches for the type of variable x in the AST. So with this find relation, we can systematically rewrite the variable reference rule to use the find relation. Intuitively, the find relation walks up the AST to find the expression which bound the name to determine its type. And in the paper, we present a systematic approach to deriving this find relation, and it's based on the structure how the context is built. Now that we have addressed this first scenario where incremental performance is suboptimal, let's have a look at the typing rule for addition to illustrate the second scenario. And the addition is not well typed if one of the sub-expressions is not of type NUT. So here we have the nested addition expression and see how the typing derivation looks like. And here it's important that E1, E2, E3, and E4 are of type NUT. And in Datalog, we cache these individual typing results for each expression. So what happens to that typing derivation and the cache if E1 is not of type NUT anymore? So we need to delete the entry in the cache, and now E1 plus E2 is also not derivable anymore, and therefore we need to delete all the ancestors of this expression in the cache. And if we change the program again, so E1 is of type NUT again, we need to rederive the typing information for all the ancestors of E1 plus E2. So when writing programs, we will introduce typing errors and we will fix these errors in quick succession. And this will result in oscillation of the cache, and this hurts incremental performance. To make the cache more resilient to changes, we have found a new encoding of type systems. And it's based on the observation that only small parts of the typing derivation get stuck. And the goal is to type as much parts of the program as possible. And we take the typing relation and derive two relations. One that derives the type, if possible, and another that collects stuck derivations. But here we need to be careful, because the well-typed criteria changes. On the left-hand side, an expression is well-typed if it is in the typing relation. But after our transformation on the right-hand side, it is only well-typed if the expression is contained in the typing relation and the error collection relation is empty, which means that there were no stuck derivations. So after applying these transformations, we measured the performance of the same programs and changes again. And the incremental update times for high impact changes improved significantly. Before, they were 1.4 to 7x, and after the optimizations, they were 7x to roughly 900x. But here we had to pay the price of having a higher initialization time, which got roughly 6 times slower. However, this is not a hard price to pay. The initialization is only done once when we start the programming editor. So in our paper, we tackled the fundamental challenges that arise when deriving incremental type checkers by translating to Datalog. But these fundamental challenges already support a variety of typing features, such as simple types, including Boolean and NUT types, parametric polymorphism, sum and product types, bidirectional type checking, and iso-recursive types. And based on this foundation of deriving incremental type checkers systematically, we want to investigate how we can support more sophisticated typing features, such as nominal typing of Java, unification-based type inference of Haskell, and dependent types of ACTA. Additionally to the transformations we already presented, we define a DSL to describe type systems. We formally define the transformations, and we specify correctness criteria for these transformations. And at last, we implement a compiler that takes a language specification and translates them to Datalog to get a fast type checker automatically. To summarize, we present an approach of deriving incremental type checkers by translating to Datalog. Our approach is systematic. To use Datalog as a target, we had to find a way of finitely encoding the typing relation. And to achieve better performance, we eliminated the context and we derived a separate error collection relation. And all of these transformations simplify the data dependencies of type systems. And these are independent of Datalog. Thank you for your attention.